Hello everyone, my name is Abubakar Mshangama. I'm an early stage researcher in the team of 5G project. This project is an European training network in the framework of MSCA Innovative Training Network of the European Commission Horizon 2020 framework. The topic of this presentation is millimeter wave beamforming for massive MIMO systems. Here is the outline of this presentation. I will first start with an overview of millimeter wave and massive MIMO, followed by an overview of beamforming, its purposes, categories, and techniques. And after that, I'll present some of the advantages of millimeter wave beamforming in massive MIMO systems. Finally, I will list up some of the challenges that have to be targeted in future researches. Here we are. As we all know, millimeter wave are electromagnetic waves that their frequency lie between 30 into 300 GHz. It can avail up to 50 GHz of bandwidth. At millimeter wave wireless communication band, carrier frequency can be reused within a short distances because of the high attenuation of signal in free space and penetration. Furthermore, millimeter wave frequency are well known of its small wavelength, which is in the range of 1 into 10 millimeter. The antennas are sufficiently small, therefore it becomes practical to construct and implement multi-part antennas arrays and integrate them onto boards and chip circuits. Owing to the transmission range limitations, in addition to the relatively narrow beam width of millimeter wave communication systems, a significant improvement in security and privacy can be obtained. On the other hand, massive MIMO is a wireless network that receives and transmits signal simultaneously on the same radio channel using different and high number of antennas at the transmitter and the receiver side. Moreover, the massive MIMO technology scale up the number of antennas elements by several orders of magnitude more than the number used in conventional MIMO systems, aiming to reap the benefits of MIMO on a much larger scale. Additionally, massive MIMO has the potential to increase the capacity of the network by aggressive spatial multiplexing and simultaneously improving the radiated energy efficiency. It is also a key enabler for the development of future broadband networks with energy efficient, secure, and robust. Besides that, massive MIMO can reduce transmitted energy consumption of the signal processing with more efficiency usage of the radio spectrum. In this diagram, we can see an example of a network using millimeter wave massive MIMO beamforming. As we can see, here we have a core network, and after that we have a macro cell base station, and it's surrounded with few small cells. Each small cell is equipped with a base station and a user terminal or a receiver. The core network is connected to the macro cell base station with a fiber optic, and it can be connected with another way such as microwave. And from the base station, the main base station, to the small cells, the connection is made by millimeter waves. the millimeter wave, it can be used for front haul and back haul. After that, we can see that as we have the user's terminals inside the small cell, they are also connected to the network through the small cell base station. Here is an example of a beamforming in a millimeter wave. As we may have many users in one small cell, but the antenna in the base station will direct the beam into the specific and intended user. This is just a small example of millimeter wave massive MIMO network. In this diagram, even though millimeter wave provide high bandwidth, which increase the capacity of the network, but it's very sensitive to blockage, such as wall and some environment aspects like raindrops. As we can see, here we have a tree here and some of raindrops. The signal is being sent from the base station. When it's been starting from here, from the base station, before facing the tree, the signal was strong, and it started getting weak after the blockage, and it gets more weaker when it faces the raindrops. This region is called Fresnel Zone. Fresnel Zone is the region between the transmitted antenna and the transceiver antenna. It is used to understand the strength of the waves. From here, its millimeter wave beamforming appears, as it's the only solution that can bring the signal at very high strength into the desired user. Next, we are going to start talking about the beamforming. Before starting with beamforming, here we have a channel model which has an input signal which is represented by X and a channel matrix which is represented by H and noise N, while the output signal or the received signal is represented by Y. The output signal is given by this equation. Next, we are going to start with the definition of beamforming. Beamforming is a signal processing procedure used with multiple arrays of antenna at the transmitter and receiver side to simultaneously send or detect multiple signals from multiple desired terminals to increase the capacity and performance of the system. Beamforming can be realized by assembling the element in an organized array in which the beams steered toward a specific direction are added and the other beams are neglected. In the next section, we are going to see the purposes of beamforming. Beamforming has so many purposes. Some of these purposes is to generate a beam of necessary shape and to direct the beam to a desired location in a real time, and suppressing the interferences. Beamforming shape radio wave through adjustment to phase and amplitude to make them more powerful and targeted. Instead of blasting coverage out through a cell, beamforming can direct the coverage where it's needed into the intended user. These are some of the purposes of beamforming. Next, we are going to see the categories of beamforming. Beamforming can be divided into two categories depending on the signal bandwidth. First one is the narrow band beamforming. The second one is the wide band beamforming. Narrow band beamforming is achieved by instantaneous linear combination of the received array signal. However, when the involved signals are wideband, an additional processing dimension must be employed for effective operation, such as tapered delay lines. Some of the applications that using narrow band beamforming are current wireless communication, which are still focused on the narrow band beamforming. However, wideband beamforming become an important topic for future wireless communication application. Some of its application, it will be the 5G network. Owing to the 5G requirement concerning high frequency bandwidth signals for achieving an extremely high data rate, the best wideband beamforming that can be implemented for this technology is millimeterwave beamforming. To make use of this, I'm going to show some of the beamforming techniques that are used in millimeter waves. Beamforming wave or beamforming techniques can be classified based on two things, either on physical characteristics or on signal processing. Based on physical characteristic, beamforming techniques can be classified into switched beam and adaptive beam. Switched beam systems realization utilize predefined number of lobes in a beam pattern and switch between them during the connection. With the advanced adaptive beamforming system, researchers successfully provide that millimeter wave spectrum can support cells with coverage radius of few hundred meters for outdoors and indoor systems with transmitted data of greater than 500 MB per second. On the other side, adaptive array, the antenna diagram changes its shapes and direction toward each dedicated user adaptively, providing more degrees of freedoms, and they are based on weighting approaches. Secondly, based on the signal processing, beamforming techniques are classified into analog beamforming, digital beamforming, and hybrid beamforming. The current communication systems are mainly based on the signal processing. Therefore, in the coming section, I'm going to explain analog, digital, and hybrid beamforming in more details. Before heading into the beamforming based on signal processing, here is an equation that represents a channel model with beamforming. This equation represents a downlink stage where the base station deploys M transmitting beamforming antenna element, and each terminal can be well appointed with multiple beamforming antenna. And here on the right side, each user here is equipped with a single antenna. And coming back to the equation, X represent the information signal for the user in the cell, while YJK represent the received signal at the user side, and HJK represent the downlink channel vector from the base station to the user in the cell, while the capital H here denote the transpose conjugate, and the WJK denote the transmitting downlink beamforming, and here finally we have the NJK, which represent the channel noise. Next, I'm going to give more detail about the techniques of beamforming based on signal processing. As I have said earlier, beamforming techniques is based on signal processing, is categorized into three: analog, digital, and hybrid. Here I have the analog beamforming. The main concept behind the analog beamforming is controlling the phase of each transmitting signal using low-cost phase shifter. A selective radio frequency switch is used here to facilitate the beam steering function. The traditional beamforming creates a single beam by applying a phase delay or time delay to each antenna element. In contrast, here we have the digital beamforming. Digital beamforming consists of many utilities, including the direction of arrival estimation, programmable control of antenna and radiation pattern, and adaptive steering of each beam and null to enhance the SINR. These advantages can be obtained only by using digital beamforming technology. In full digital beamforming, each antenna mandates a dedicated analog baseband channel, which in turn calls for a digital transceiver for each antenna, but this will add to both cost and power consumption. On the other hand, a hybrid beamforming concept is just like a combination of digital and analog beamforming, which is widely applied in massive MIMO system. The digital beamforming portion creates a baseband signal, whereas the analog beamforming portion addresses the radio frequency effect by reducing the number of analog to digital converter and or digital to analog converter, which improve the output of power amplifier. After this one, I'm going to give some of the beamforming detector techniques which are used in massive MIMO systems. First, I have maximum ratio combining, and next I have the minimum mean square error, and finally there is the zero forcing techniques. I'm not going to go in details in this, I just wanted to mention them. In the coming section, I'm going to give some of the advantages of using beamforming in massive MIMO system. Massive MIMO systems are assisted by beamforming process to reduce the power consumption of the entire system by computing the optimal quantity of antenna element that meet several essential criteria for manipulating energy efficiency massive MIMO system. On the other hand, the concept of beamforming is to steer the transmitted signal toward the intended user. Therefore, the receiver will be the only path to recover the wanted signal from the overlay signal, therefore improving the spectral efficiency and enhancing the energy efficiency. Besides that, beamforming will help in getting rid of path loss, channel noise, and crosstalk, while reducing the system designing complexity as well as the operational cost. Finally, I'm going to mention some of the challenges that millimeter wave beamforming in massive MIMO system have to be targeted. Some of these challenges is to design an efficient hybrid techniques for wideband multi-user millimeter wave systems, and to propose a reduced complexity techniques in which the hardware complexity is optimized, and finally to efficiently estimate the channel state information at the base station side. That was all for this presentation. For a small reminder that TeamUp 5G project has received funding from the European Union Horizon 2020 Research and Innovation Program under the MSCA Curie